Okay. Yeah, then let's start. So, what we have studied in previous class, that we have studied that not only this logistic equation has something the means this logistic equation and bifurcation diagram looks similar to the bifurcation diagram or orbit diagram of the a complicated looking graph. This is sine for r sine pi xn. So for both of these two cases the bifurcation diagram looks similar. Not only that, the appearance of the periodic orbit or fixed points periodic cycle, so one periodic cycle, two periodic cycle, four periodic cycle, so this is called the metropolis U sequence, and we have means it has been greatly studied that this sequence of appearance of periodic orbit is very common to not only for this logistic map but also for any kind of map which generate the chaos by the period doubling bifurcation. So and there are we have talked about BZ chemical reaction, and this is where the experimental verification of these things actually successfully done. Now we want to say something which is quantitative. We want to say something universal, not particular to this logistic map, but also to any kind of period doubling root of chaos. So it is similar like the value of pi. So we are wanting to find such universality. So if anyone draw a circle, whatever its size doesn't matter, but if anyone tries to get the ratio of its uh, uh, twice of radius and its what is the circumference. So suppose it's the length of the circumference is s by 2r will be always equal to a irrational number, that is pi. So this is the signature of a circle. So this is quite universal for, this is actually universal for any cycle. So similarly, in today's class we are going to see, is there anything like this irrational number related to this period doubling bifurcation which bears the signature of this period doubling bifurcation. Now so let's see. So this is called the there is some constant which is called Feigenbaum diagram. So this Feigenbaum is a famous person in this chaos, because Feigenbaum in 1980 he published a paper. That paper contains that's actually he by by this renormalization method he find out some constant which is universal. So first of all, Feigenbaum means there is a good story in the Stoker's book about the things how the serendipity by means by chance what how Feigenbaum find this constant. So it is a very worth to read. So you can go to this Stoker's book at page number 408. You will see that there is a short story. So I am not going to the story, but what he have found that first through his numerical and this functional theory method, renormalization method, what he found that, so suppose this is some system which going to period doubling route of bifurcation. Suppose first it doubled, then again some point like this, some point like this happen. So this kind of, now what we found that the fast period doubling, suppose this is the r axis, so fast period doubling happen here at suppose r1, and the second period doubling happen in suppose r2, and third happen at r3. We actually know these values for logistic map, so let me rewrite those things. So for logistic map, this r1 is exactly 3, we have calculated that, and r2 is actually 1 plus root 6, that we have also calculated, so it is 3.449, r3 is 3.5409. These values you will get from this Stokes book, and you can calculate also from this if since we know how to generate this orbit diagram, and from this orbit diagram you can actually know quite close value of r1 at which the period doubling bifurcation happens. So that is the thing, but one thing you notice that the difference between these r1 r2, the difference between this r2 r3 is lesser than r1 r2. So from here also you can see this is the difference between the r2 and r3 is 0.449, but for r2 to r3 the difference, so let's do it. So suppose r3 minus r2 by, or do it in other way, so do it like this, suppose r2 minus r1 by r3 minus r2. So this will be 3.449 minus 3, 9, 3.449 minus 3.4, 3.54409 minus 3.449. Now let's calculate what its value is. 3.449 minus 3, that will be 0.449, 3.54409 minus 3.449, 0.0959, 0.449 divided by 0.0609509. It is coming out that it is equal to 4.72. That means you see, and if you calculate the value of r3 and r4, and if you calculate this, suppose this is delta prime, so if you calculate this delta prime for every this value, you will find that this difference between this r1 and r2 actually decreasing, means it's called decreasing geometrically, or it is converging geometrically to a particular delta. So the value of delta, you see this 4.72, this means this R2 minus okay, give me 1 minute, I have to take a call. হ্যাঁ বলতো ভাই আমি এখন ক্লাসে আছি, আমি ক্লাস নিচ্ছি, দাঁড়া আমি 12টার মধ্যে ক্লাস শেষ হবে। হুম, হ্যাঁ 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 হ্যাঁ। So, sorry Subbusaji for the interruption. So, can you hear me, Subbusaji? Hi. So, previously I was not audible, right? Because I have found that I just my microphone was off there then. So let me start it again. Subbusaji, are you there? But means I was not audible, right? But I just now find. Okay, okay. Then it's fine. Then it's, okay, okay. So then means at the time this Feigenbaum was not quite capable of using the computer the way we are using now. Uh, so what he discovered something, and he just made up some his own version of computer, and he just calculate these values R1, R2, R3 from these generating function theory. So that's the story you will look upon at this book. Now, what is the thing we are talking about? That these the these series, this the difference between R2 minus R1. Okay, let me rejoin because okay, let me rejoin in this meeting because I have taken a call. That's why maybe it is breaking badly. Okay, let me. I guess now it is fine. I probably the network knows that we are dealing with the chaos. That's why the background chaos is there. So apart from the joke, yeah, that okay. So you see these the distance between the first period doubling bifurcation occurs at which point, and the second period doubling bifurcation occurs in that point. The third period doubling bifurcation occurs at 3, but the distance between these R's actually decreasing, and you will means Feigenbaum find that this is very interesting, that this ratio, that the geometric ratio at which this is actually decreasing, it actually going towards a number when we increasing these values in. So you will see this is at the first point it actually getting 4.72. So it when you will get this limit n tends to infinity, this is actually value of delta, this is r n minus 1 by Rn plus 1 minus Rn, you will found that the value is exactly 4.669, and you from the first the first this ratio we can the value we actually getting is 4.72, which is very close to this ratio when n going to infinity. So this is not a rational number. This will continue this whatever your how much your precision will be, that will actually decide that how much means you will get means you get to know this number. So, and Feigenbaum found that this is not only the case for logistic equation. So in place of this logistic equation, if you can find the values of R to Rn, and which actually Feigenbaum by his own hand have done this calculation. So at the time when he was dealing with this period doubling bifurcation, he came to know that not only this logistic equation go through this period doubling root of chaos, but there is another map which is sign map that we have seen, that the orbit diagram we have seen and compare with the logistic equation, logistic map, and he came to know that sign function also goes through a period doubling root. And actually what he found that these, when he calculated these the values of the point at which this period doubling root of bifurcation occurs, they follows exactly the same thing. And if you calculate for this sign map also, you will get when limit n tends to infinity, this Rn minus 1 by Rn plus 1 exactly equal to 4.669. so it's looked like that no matter what map you are using, it's like similar to the circle. So where it doesn't matter how big a circle you are drawing, what the mathematician found that the ratio between the circumference and the twice of this radius is always come the value pi, an irrational number. So it is that the pi is the signature of that circle. It's similarly that this value delta 4.669 some other irrational number which is actually signifies the period doubling root of the chaos. So that's why it is universal. So universal in a sense, this constant in physics is called the universal, since it is universal in the sense like that the pi in the case of circles. So this is not only the first universal constant, there are another universal constant, so which is so let me recall one thing, then I will go. So first recall this superstable orbit, so we know, means we have the definition we know. So we know that what is the stability means. Stability means if I derivative if I took the first derivative of any function, so modulus value of that function if it less than 1, then we call this function is stable at near about the fixed point x equal to 0. Now what is the minimum value that it can take, since it should always be positive and it has to be less than 1, so what will be the minimum possible value it can achieve? So that will be x0 equal to 0. So if any orbit contains a fixed point, suppose xm, any fixed point xm whose first derivative is 0, then the orbit is called the superstable orbit, because it contains a fixed point which is superstable. So now for the logistic equation, we know that what does it mean. So for the logistic equation, we know that f prime x is r into 1 minus 2x. So we know that if any orbit contain xm equal to half, then this first derivative of this is 0. So that means if it contain xm equal to half, that will be the super stable orbit. Now if I draw we know that something like, let me draw arbitrary orbit some orbit diagram. Something like that. Now suppose this is that point xm. So if I draw, so my drawing is very bad, so I draw xm. So suppose xm is like that. Okay, suppose xm, this is the y, this is the, suppose this is value 0.5, this is 0.5. I am taking a draw a line, so this is 0.5. Now suppose it hits here 0.5, I don't know. So now one thing you actually notice that the distance between where this 0.5 cuts, that means the here we know that it is a true period orbit. So what is the distance between the other period from, since we know that these two period orbit contain one point which is super stable, which we actually know that is xm. So what is other value is, suppose we know this xm, so what is the other value of the periodic point? So that is this point, so this point. So now it has a super stable two period orbit. Now what is the distance between these two period? Now the distance between the two period is, suppose, dn, the distance between the two period. Now when the next period doubling bifurcation occurs, so here, so then also a super stable orbit occurs. So now here, what is the distance between these, what is the distance between the orbit 2 point, what is the distance between the orbit of the 2 point in a super stable orbit? So that will be this point and this point. So this in the period doubling orbit, period doubling here, from this table fixed point become unstable and two other point created. So what is the distance between the 2 points? So that will be 2 point of orbit, that is actually, suppose it is some after some nth bifurcation, and this is the n plus 1th bifurcation, n plus 1th bifurcation. So it is actually n plus 1. Now you see that this distance between the distance between these 2 point of a super stable orbit actually decrease, means it is not in the quite same manner as the previous one, but it is actually decreasing. Now Feigenbaum what actually also found that this is not quite decreasing in not quite a random manner, but if you find that dn, this distance by dn plus 1, so that means this distance is also decreasing geometrically. And what Feigenbaum found, that if I goes to infinity, so this is alpha, so this is infinity, my infinity look very bad, so this is infinity, so is equal to minus 2.5029. So this is another irrational number what he found that this is also a signature of the period doubling root of bifurcation. Why my negative sign? So previously you see that the other point of the orbit was above the xn point, but here it is the below the xn point. So that's why it is negative, signifies that the previously it was one side of this xn, and in this means suppose previously the other fixed point or other point of the orbit is slightly higher than the xm, and in its consequent in subsequent iteration the orbit of the superstable is just below to the xm. So that's all. So this is the two constant which is called the universal to this period doubling root of bifurcation, and that's all. Now we are going to use a little bit of renormalization theory to see this the self similarity, and by studying the self similarity we want to find out this constant, and let's see how much we can go. And we also want to means up to now we know that there is happens something period doubling or period doubling bifurcation, but there is no way to calculate this. There is a way, but we don't know the way to calculate what is the value of r1, what is the value of r2, what is the value of r3, other than using a computer. So we will see that. Let's see the first let me show you the self similarity because of which this renormalization is possible. Okay, basically let me show you self similarity. So Busachi, is it clear that up to now whatever we done, so is it clear what universality means for this period doubling root of chaos? Okay. Okay, where it was. Oh, let us show from first here. So this is the thing. So here you can see one thing, that if I go here, so if I see from this point, so you will find that from this point the orbit diagram looks that from there is a twig, then the means it's look like a branch of a tree, so it's actually called the figure tree. This is also called quite famous as a figure tree. So because this quite similar to that the branches of a tree, if you notice that the branches of a trees actually bifurcate in the similar manner as you will see in this case. So you can, if you want to find that the what is the value of the constant there, you will also quite find the similar values, because this is also kind of period doubling root of bifurcation. If you see that the structure is like the same as what I am showing here. But one thing is very interesting here, that is if you observe the figure tree from this point, you will see that there is a something like that, and then two branches appear from, and then from these two branches another two branches again are going outside. Now what happens if instead of from observing from this point, if I now try to observe from this point, now you find that the similar structure is there. So something like going from this point to here, then two branches appears, then from that two branches again other two branches appears. Now for of what is the difference between observing this point and this point. So the observing from this point and this point look actually similar, but what happens, so only problem is the distance along this if we say r axis, so it got tinier, means previously the structure look very big. Now if I start from observing here, the structure look very smaller because it got reduced, because you see that the distance between these points reduced, so that's why you see the distance between this point also reduced, so it scaled down, so it become tinier, scale down in y direction as well as in this r direction or x direction. So from here to here the distance between this and this also decreased, that's why this distance between this is also decreased. Now not only that, so if I go here also, from here also if you see the structure is similar. So from here you will see something goes above first, then there again two branches, from the two branches again two branches will come, and only difference will be that the it become again smaller than this one. So previously the structure was this much, then the structure become this much, then the structure will become this much, but inside the big black circle, whatever the system was is the same is with this blue circle and the same with this green circle. So that means the system actually contains infinite copies of self-similar objects. It is called the self-similar object. So only thing is that the self-similar object is little bit tinier and tinier when we go towards little bit lower scale. So from that's where it is called the renormalization. Means the theory is, if I instead of start from here, if I start from here and if I make it bigger in both in y direction and x direction, we in principle we could create this whole the structure which is remain inside this black circle, and so that is the theory of the renormalization. So we will study now the renormalization. So let me first show you some bifurcation diagram. So this is not handwritten, hand drawing, but it is a computer generated the bifurcation diagram. From here you can also see that the first observe the distance between this, the first period suppose here first period doubling occurrence and the second period doubling occurrence, the distance much longer, but when you will see the second to third, the distance is got decreased, and third to fourth got further decreased. So distance actually decreasing. Now one thing whatever I was talking about, so if you start from here, you see that the some twig like structure happens, then there are two branches and two branches got into four another branches. So instead of this point, if we focus from this point, so you also find the same structure, only what you will find that previously it was in the above of this xm line, and now it is only the below of this xm line. So previously this is the same as the previous one, but only tinier. Now again, if I start instead of this point, if I start from this point, you will see that no, it is similar to the previous one, only just reverse to this direction. So it was below, it was upper. So this kind of structure will going to infinity and will hit the R infinity at some point. So that is the self similar picture of this bifurcation diagram, or the so that motivates us to renormalize the thing. So if I take this smaller piece here, and if I renormalize, we could generate the whole structure again. So that's all. That is the self similarity means. Now, Subbosaji, is it clear that what the why we are doing the renormalization? No. Hmm. 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 Yeah. It's a fractal, and you also can see a fractal in our screen, that this structure is repeating but becomes smaller and smaller and smaller and smaller and smaller. So can you see now screen in computer screen? Oh, my computer screen is not visible. Okay, in my computer screen, if you see that the same structure, first the bigger structure, the participant, the bigger structure appear, then the same thing appear in a smaller version, then same thing appear in the another smaller version, tinier version, then another tinier version. So it goes to infinity. So this is a self similar structure. So that's why, if you can see, then it will be very more ah ah so this is the thing, is also happening here, but only it become tinier and tinier whenever means in the next generations, just like the screen of our computer. So that's it. Now let's see it from the perspective of these functions. So what part we actually are talking about? So let's see. Now, okay, this is not true. Okay, give me some time. To show you, well, okay, it is actually. So here I am using a map, which is here I am using a map which is f x r is equal to r minus x square. This map I am using here, and from here one can find easily what is the point at which the first period doubling bifurcation will occur, and the superstable, first it will contain a superstable orbit. So if you derivative it, f prime x, that will be 2x, so minus 2x. So when it will become 0, so x equal to 0. So at if any orbit contain x equal to 0, that will be the superstable orbit. Now what will be its r0 when the creation of the first means creation of the first superstable orbit. So that will be when x will be r minus x square. So from here what you will get that now at which value means now if you want to calculate at which value of r these x will become 0. So let put x equal to 0. So you put and you will get r equal to 0. So you find that at r equal to 0 the first superstable orbit you will see, and then you will again from this same thing, but if you do this f square x r, you will find that r minus x square this you will find. Now when what will be this fixed point if it is equal to x? Now we know that it should contain a point which is x equal to 0. If I put there, so it left me this equation r minus r square equal to 0. So this I got r into r minus 1 equal to 0. So we know that it's at r equal to 0 the first superstable orbit come, but at r equal to 1 you will find that the second superstable orbit it will occur. So these example you actually find in this Soga's book. So I am not going deeper into this. So that's why. So what I am plotting here. So at r equal to 0. So r0 means r equal to 0. I am here plotting this function. This r minus x square. Now what you will find that this is, and I just do one thing that I again plot the f square x r1. R1 means at r equal to 1 I am plotting the same thing, but at the value r1 and the map f square. Now you find one interesting thing that the whole f square is not similar to this whole f square is not similar to this fx map. So but so if you find that here this fx map there are two fixed points, one is at this point and this point. Now if I focus so only this part of this map, so if I focus this is a fixed point, so suppose that this fixed point is similar to this fixed point and this fixed point is similar to this. So if I focus only into this part of this map, so let me do it. So this part of the map, so if I only focus to this part of the map, okay, if so now I have focused only that only part where this is f square x, but only this smaller part that we are showing here. So the fixed point, unstable fixed point to this point. So this point is looking quite similar to this, but what you find that this the value of this means in it reduce in both y direction. So the from here to here if you measure it become 0.5, but here to here is 0.1. So it is bigger in longer in y direction, and it's also smaller in x direction also. You see that it is -1 to +1, here minus 0.05 to 0.5. So it is also decreased, squeezed in x direction and y direction also, but it looks similar just in opposite sense. But now if I renormalize it in this fashion, so if I renormalize this, okay, so if I renormalize by some number, suppose if I put x equal to 1, when I put x equal to 1, it should put that this point to -1 here, and when I put x equal to -1, it should put this point to here, and when I put x equal to 0, it should put this point to some means the length of this is 1. So this is the renormalizations. If you see, when I, so I don't know, yeah, you can see maybe. So when I renormalize it, means when first what I did, I draw, let me do again step by step, then it will be much more clearer. What I am showing here is the self-stimulus structure. So here you see the fxr0. This fxr0 is okay. Let me draw it. Then it will be much more convenience. So let me draw it here. So suppose there, what the problem is. Suppose okay, this is okay. Now this is suppose middle of this thing. Suppose this is f of x or 0. Now let me copy same thing here. Okay, we do one thing. So maybe this is okay. Suppose this is f square. Suppose this is f square x. So this is f square x at r1. You notice that since this is suppose xm, so both of these contain this fixed point xm, this fixed point xm. So both of these orbits are superstable orbits, since both of them contain a point xm at which the tangent is tangent is parallel to the x-axis. So that's all. Now from here what we will see that whatever this means whatever inside this big box is looking exactly same as drawn in this smaller box. So this the graph in the, so my drawing is very bad, but if I so like this, okay. Now the smaller box, the thing remain in between the smaller green box is actually similar to whatever remains inside this box. What happens? So we only squeezed from here. You can see this box and this box at same size because I copied this box and paste here. So what is happened here? So it the x-axis, actually, if I squeeze the box, if I squeeze this box in x and y direction and put it inside this region, it will become similar to this diagram. Now if I want to create a bigger box from here, what I have to do? I have to multiply this axis by some bigger number. Or one thing we can do, that from here we know that suppose is this distance, suppose we know that this distance is, we know actually this distance, what this distance means. So we know that this is, we know these 2 points will be the stable fixed point of the superstable orbit, and from here we know that this orbit, the superstable distance between the superstable orbit, maintaining a something, the ratio is maintaining something, a ratio which is actually universe, which is minus 2.5029. So the distance between this point and this point, so if I draw here, if I draw it here, so distance between these 2 points, actually here and here, so this distance, actually the ratio of this distance we know. So and suppose that this is the in middle of that 2 point, then here to here the same thing is here to here. So now if I want to create the same thing like this, what we have to do? We have to normalize here. Normalize means we have to zoom, we have to bigger this y-axis, so that means we have to multiply this f square by some constant, and here x goes from suppose here -1 to +1. So here goes to -1 to +1, but it can't goes to -1 to +1. It should go from here to here. Suppose this is -1 by a to +1 by a. So this is smaller than 1. So this is x by a. So if I put x equal to 1 plus 1, it will go to 1 by a, and if I put -1, it will go to -1 by a, comma r1. If I put it here, it should look exactly like this. So this is my first thing. Sobosaji, is it clear? Is it clear to you? Means how I getting structure? Exactly. Exactly, it is flipped. So that point I am going to talk about. So it is actually flipped. That's why what we have to do, we have to reverse the direction of x and y. So we have to take this point to -1 by a and this point to +1 by a. What we have to do? So we have to take this a as -a or negative number. If I take this a negative, so what happened? This point will flipped, because if suppose this is 0, if I taking this is 0, so if I flip this, so previously it was negative, now it will become positive, and now this point will come here. So if I take a is a negative number, then all the problem will be solved. So we have, so the same thing we have done here. So we have what we have do here, that so we calculated what is the distance between this and this, and we have found that the distance is 0.62. or something like that, 0.62. Now if I that thing that this is alpha is 0.1 by mine, I have taken alpha is negative 1 by 0.62. So if I take that, so if I take that thing, what you will find that I am only here zooming out only this region. So a into f square x by a, where I have taken a is minus 1 by 0.62. So you will find that these two structure, the first and the third structure, is looking exactly like same to each other. So this is the self-similarity. So but here this function is f x r0, but here this function is some constant f square x by a comma r0. So these two functions are different, but they are looking similar to each other. So as if this f square x r1 contain a copy of f x comma r0 in a tinier form. Now is it clear, Subhasaji? Exactly similar. So what this a I have taken, so I have taken the a, what is the distance between this point and this point. So suppose this point and this point distance, so this point you will find that it is 0.0 and this point is 0.62. So I have taken a is minus 1 by 62. So that's where minus 1 by 62 will be greater than 1. That's why the y actually get longer. So that's why you get from the same scale, and x by a is reduced by something, so that is minus 1 to plus 1. So whenever you will do it by your own means in you, by yourself, you will get it, the feelings you will get much more clear. So now mathematically what does it mean? Mathematically means this f of x r0 is quite similar to a f square x by a r1. So this is the basic thing of the renormalizations. So what we done? So we done renormalize the function of f square r of the little bit region. So if I zoom out, so it is called the zooming out. So if I only zooming out this smaller region, this x by a, so x by previously the region was plus 1 minus 1 to plus 1. Now our region is minus 1 by 2 plus 1 by a. Now since we are zooming out this region, and if I zooming out and if I multiply by a, then these two structure is looking same. This is called renormalization. But in the renormalization, one thing you have to always keep into your mind, that you have to change this parameter. So the all for the all parameter value, it is not exactly look same as this one, but only if I change the r0 value to r1, then only the structure will become self similar. So we have to shift the value of r0. Now why should we keep stop here? Because from here, since it is looking same as this, so from here one can generate, suppose if we take this is a function fx, so from here you can generate another f square x. That f square x should be self similar to this point. So that what I am saying, that if I f square x by a r1 should be self similar to alpha into f4 to its period doubling orbit, again x by another alpha decrease, alpha square R2. So similar to this, we can generate f square R1. Similar to from here we can generate again another f square. Is it clear, Subhutaji? Now this step. Okay. So similar to this way, you can means this is x comma r0 is quite similar to alpha square f4 x by alpha square r2. Now if I go in this way, suppose f of x r0 should be similar to alpha to the power n f of 2 to the power n x alpha to the power n comma rn. Now limit n tends to infinity, this function fn f 2 to the power n x by alpha n comma rn will be a function called g0x. Now this is g0x is again a universal function. This g0x does not depend on the form of f square x. It does not depend on whether it is the fx is logistic or 1 minus x square. It doesn't depend on. And what the thing this universal function depends, it's actually only depends on the what is the maximum order of the x here. Suppose in the case of logistic, you will find that x into 1 minus x, so this is quadratic, x minus x square. So it's only depend on in the power, highest power of this function. So if it instead of quadratic, if it become some cubic or some other, it will get another result. Suppose this like a thing x square minus x4, its maximum order is x4, then this function will change. So it will only depend on the exponent of the highest exponent of this map. So this is the renormalizations. From the renormalizations in the next class we will find out what is the value at which the first bifurcation or nth bifurcation occurs, and what is these values of these alpha and delta. Now here one thing, so this here we are using a. Now it has been found that this a has to be equal to the alpha that we have get here, that this alpha, because this is the thing that is reduced. This is the ratio that alpha is 0 minus 2.5029. So this is the scale by which we are compressing the system and put the structure into itself. So this alpha should be equal to this alpha. So in the next class we will see that. That's all. So if you have any questions, you can ask me. Okay. Yeah, okay. So you see, previously we don't know and we cannot predict theoretically what is the value at which the period doubling bifurcation occurs. What is the magnitude of the R1? What is the magnitude of the R2? What is the magnitude of R3? We are always saying in words. So there it will means period doubling bifurcation occurs. Although we can use a computer and do a numerical analysis to find out that, but our question is that is there any theoretical method by which we can say that at which point the first period doubling bifurcation will occur? So this is the motivation for doing this renormalization. By this renormalizing this thing, we will in the next class you will see that how we can find out these values, these at which the period doubling bifurcation occurs. and you can also find out that what is this value of this universal exponent. So why means the renormalization actually says you the why this universal constant are universal. Why it does not depend on the function, what the functional form of this. Suppose it can be logistic map, it can be sign map, but why for all the map it's came same, that this universal constant, so that you will get it from here. Hmm. Oh, okay. Okay, thank you for joining. Now I am leaving this class.